Welcome back to the next lecture on vibrational partition function. In the previous lecture, we have talked about what is the expression for the vibrational energy, and then we discussed about how to set the ground state vibrational energy equal to 0, and then how to account for if we want to overall calculate the internal energy. So, let us take a look at what we have discussed earlier. We talked about this is the overall expression for the vibrational energy levels, where V, which is the vibrational quantum number, is 0, 1, 2, etc. And EV is equal to VHC nu bar, where when you set V equal to 0, energy levels for the ground state are set to 0. So, let us now discuss further. QV is equal to summation V from 0 to infinity. You have exponential minus V, I will put beta HC nu bar, which you can write as is written above, or if you do not want, you can leave it as such. So, I have now QV is equal to, when V is equal to 0, exponential 0 is equal to 1 plus exponential minus beta HC nu bar plus exponential minus 2 beta HC nu bar plus exponential minus 3 beta HC nu bar plus so on. Now, you remember, let me just give a background. We had EV is equal to VHC nu bar. So, that means E0 is equal to 0, E1 is equal to HC nu bar, E2 is equal to 2HC nu bar, E3 is equal to 3HC nu bar, etc., etc. And if you look at the difference between this and this is HC nu bar, difference between this and this is HC nu bar, difference between this and this is HC nu bar. So, that means difference between the successive energy levels is HC nu bar. That means this difference is HC nu bar, each one is HC nu bar. And if you set this HC nu bar, if I just write this to be equal to E, then you have E, 2E, 3E, 4E, etc. So, this becomes a uniform ladder of energy levels. Remember the approximation here. We are considering that the vibrational excitation is not too large. Therefore, we are using the harmonic oscillator approximation. So, therefore, this is the same case as that we have discussed earlier when we talked about uniform ladder of energy levels. So, let me come back to this discussion, and if you look at the sum, it is 1 plus exponential minus beta E plus exponential minus 2 beta E plus exponential minus 3 beta E, which can be written as QV is equal to 1 plus exponential minus beta HC nu bar for V equal to 1, for V equal to 2, this second term I can write minus beta H C nu bar square plus exponential minus beta H C nu bar cube plus so on so on. And if I just represent this as x, this whole as x, then QV is equal to 1 plus x square plus x cube plus so on so on so on. This is sum of a GP, and sum of a GP, as we have earlier discussed when we were discussing uniform ladder of energy level, it is 1 over 1 minus x beta H C nu bar. This is the expression that you are going to use to calculate or to determine the value of vibrational contribution to partition function. Remember that we have used only one approximation here, and that approximation is that we have considered the system to be harmonic oscillator, which has led to this uniform ladder of energy level, and we have not used any other approximation. So, for a given vibrational wave number, you will have a vibrational partition function. If the vibrational wave number changes, you will have another value of vibrational partition function. The overall value of vibrational partition function will be equal to QV 1 into QV 2 into QV 3 etc., as we have discussed earlier. So, within the approximation of harmonic oscillator or uniform ladder of energy level, we can use this expression exclusively at any temperature, and we can now discuss the conditions, what happens when the temperature is very high, what happens when the temperature is very low, can we further modify this expression. So, just a recap, as I discussed in the previous slide, that you can treat within the harmonic oscillator approximation, you can treat the system like a uniform ladder of energy levels, which gives rise to equally spaced infinite array of energy levels as shown over here, and a harmonic oscillator has the same spectrum of levels. That is what I have been discussing. And our discussion of expanding this, I will just quickly once again write for the benefit of all. When V is equal to 0, then it is 1 plus exponential minus beta H C nu bar plus exponential minus beta H C nu bar square plus exponential minus beta H C nu bar cube plus so on so on. That is what it leads to, and this leads to this result. That is what we discussed in the previous lecture. That means this expression now we are going to use for calculation, for determination of vibrational contribution. With this background, let us move further. Now, there can be different conditions. For example, if we consider the vibrational wave number which are very, very high, that is, if beta V H C nu bar is much higher than 1. Let me make a simple correction over here. This V is not there. So, you treat this as 1 over 1 minus exponential minus beta H C nu bar. V is not there. Okay, so make that correction. So, same thing I will put over here, which is equal to 1 over 1 minus exponential minus beta hc nu bar. So, if beta hc nu bar is much greater than 1, then what happens? If this is much greater than 1, then exponential minus very high quantity, you can ignore that. That means, in that case QV is going to be approximately equal to 1. That means, we are talking about if the separation is very high. In that case, you will have mostly the contribution due to ground state only. That means, when you talk about vibrational levels, most of the molecules will be there in the ground state only, and in that case the vibrational contribution is going to be 1. So, when I put this condition, that means I am talking Kt is much less than Hc nu bar, right? Beta is equal to 1 over Kt. That means, we are talking about here temperatures which are very low compared to the Hc nu bar, or Kt is much lower compared to Hc nu bar. Example, for example, take methane molecule, and in the methane molecule the lowest vibrational wave number is 1306 centimeter inverse, and when you use room temperature, let us say 25 degree centigrade, then the value of beta Hc nu bar, you can put the number, h is Planck's constant, c is speed of light, and nu bar is the wave number, and when you put the numbers, it turns out to be 6, and exponential minus 6 is 0.002. So, that means 1 over 1 minus 0.002 is approximately 1. Okay. So, therefore, if the temperature is very low, or if the wave numbers are very large, in that case it is understood that the value of vibrational contribution to partition function for that normal mode of vibration is going to be close to 1. And the reason is given over here just in the form of a short calculation. Now, what happens if beta Hc nu bar is much less than 1, or Kt is much higher than beta Hc nu bar? That means, we are talking about high temperature now. When the temperature is very high, then I have Qv is equal to 1 over 1 minus exponential minus beta Hc nu bar. This is very small, right? And if you treat this beta Hc nu bar as x, 1 over exponential minus x, if x is very small, then you can expand this 1 minus with this exponential minus x in this form, 1 minus x plus x square minus x cube by 3 factorial, etc. It will come the square terms, cube terms, because it is anyway small, the square of small is further small, cube of small is further small. So, all these higher values can be ignored. So, what you are left with 1 minus beta Hc nu bar. So, in that case, what I have is here 1 over 1 and 1 get cancelled. I have beta Hc nu bar only, and beta is equal to 1 over Kt. So, when you put beta is 1 over Kt, you have vibrational contribution as Kt over Hc nu bar. I want to highlight two results over here. One is this one, where we wrote Qv is equal to 1 over 1 minus exponential minus beta Hc nu bar. This can be used at any temperature. There is no need to worry about whether the temperature is low, temperature is high, wave number is low, wave number is high, nothing to worry about. You can go ahead and use this expression. However, when the temperature is high or when the temperature is low, you need to worry about. If the temperature is low, you cannot ignore that. And anyway, we have shown if the temperature is low or if nu bar is very high, then QV is approximately coming to be 1. However, if the temperature is high compared to energy separation, in that case we show that QV can be approximated by KT over HC nu bar. When we can use this result and when we can use this result? This result can be used anyway, as we just discussed, at any temperature, but this result when can we use? In order to use that, we will come to that what temperature can be used over here, but you see, if I write QV is equal to 1 over 1 minus exponential minus beta HC nu bar. If the temperature is very low, for your simplicity I will write this also 1 minus exponential minus HC nu bar by. So, if the temperature you see is very low, when the temperature is very low, then exponential minus very high number can be ignored. In that case, QV is approximated by a value of 1. I hope it is clear. Temperature low, this number is high, exponential minus high number can be ignored. So, QV is approximately equal to 1. If the temperature is high, what did we have? We had the result we just derived, which is KT over HC nu bar. So, KT over HC nu bar. That means it is when KT is much higher than SC nu bar. This is what was the condition, that is KT is much higher than, let me correct this, KT is much higher than HC nu bar. All right. So, look at the comment. The vibrational partition function of a molecule in the harmonic approximation. Note that partition function is linearly proportional to temperature when the temperature is high. When temperature is high, you use this result, and this result basically, QV is directly proportional to temperature, K is constant, H is constant, C is constant, nu bar is constant for a given mode, and then it is almost linearly dependent on temperature, right. This is expressed in terms of KT over HC nu. But then again, bringing back the same issue, that at what temperature or under what conditions of temperature we can use this approximation. For that, it is a good idea to introduce a temperature which is called characteristic vibrational temperature. How to introduce characteristic vibrational temperature? We had QV is equal to KT over HC nu bar. So, you can mathematically show whatever I am going to discuss that now. Characteristic vibrational temperature is introduced by writing this equation. K times theta V is equal to HC nu bar, where theta V is the characteristic vibrational temperature. That means, I write theta V is equal to HC nu bar by K. We can calculate this, you can work out the units of this, it will turn out to be temperature unit. You calculate this theta V, and on the other hand, we have, let us say, experimental temperature. Experimental temperature, which is T. Now, if temperature T, experimental temperature, is higher than theta V, then you can use this approximation. So, that is the utility of characteristic vibrational temperature, that is, it is the temperature above which this approximation is valid. And since we have defined the characteristic vibrational temperature theta V as h c nu bar by k, then I can write for h c nu bar by k, I can write theta V. That means the vibrational partition function then becomes T by theta V. So, now we have three forms of vibrational contribution to partition functions. One form is, let me write down again, V dot QV is equal to 1 over 1 minus exponential minus beta h c nu bar. Second form, V dot 1 over beta h c nu bar or is equal to kT over h c nu bar. Third form, we had basically a modified form of this, which is T by theta V. And we have discussed in details under what conditions to use this, under what conditions to use any of these. This one can be used at any temperature, at any wave number. The only approximation in deriving this was we have used harmonic oscillator approximation. That is, the vibrational is not too much, vibrational excitation is not too much. And then when the temperature is high or weak bonds, in that case we got this expression which can be used. However, in order to use this expression, what you need is to find out the characteristic vibrational temperature and see if the experimental temperature is much higher than the characteristic vibrational temperature, then only you can use this approximation. And then by using the definition of characteristic vibrational temperature, we define that QV is also equal to T by theta V. So, therefore, these are the different means, these are the different ways of evaluating, of calculating or of measuring the vibrational contribution to partition function. So, what we have discussed in this lecture and the previous lecture is how to calculate, how to measure the value of vibrational contribution to partition function. First, we discussed that there can be more than one normal modes of vibration. The overall value of vibrational contribution to partition function will be equal to multiplication of each mode of vibration. Then how to evaluate each normal mode of vibrations contribution to partition function? You can use any of these three equations depending upon the temperature. So, now we are equipped with evaluating the partition function for translational degree of freedom, for rotational degree of freedom and for vibrational degree of freedom. We will make the things more clear by solving numerical problems for each case before we switch over to electronic contribution to overall partition function, and that we will do in the next lecture. Thank you very much.